Elon Musk just announced one of the most audacious industrial goals in human history, and no, it's not colonizing Mars, at least not directly. SpaceX is aiming to build 115 Raptor 3 engines every single day. That's 3,500 a month. A staggering 42,000 engines per year. Take a moment and let that sink in. Right now they're barely making one engine a day. Scaling from that to mass-producing nearly 100,000 engines a year isn't just bold, it's nearly unthinkable. And yet, that's exactly what Elon Musk is setting into motion. If it sounds like something out of a sci-fi epic, that's because it practically is. This plan represents a radical shift in how humanity approaches aerospace manufacturing. It means moving beyond the age of custom-built rockets and into an era of industrialized spaceflight, where interplanetary transport vehicles are built in numbers rivaling commercial aircraft. The vision is staggering, and it demands a level of manufacturing power that not even Boeing, Airbus, or NASA have attempted. It begs the question, how in the world does SpaceX expect to make it happen? Can this goal become reality within the next 5 to 10 years? Or is this another one of Musk's famously optimistic timelines? To answer that, we need to look at what SpaceX just revealed, a radically redesigned version of their iconic rocket. It's called the Next Generation Starship, or Next Gen Starship for short. While it stands only about 2 meters taller than its current counterpart, it's packed with upgrades that hint at how serious this ramp-up really is. For starters, the basic layout remains familiar. 6 engines on the Starship upper stage and 33 engines on the Super Heavy booster. But the story doesn't end there. This new version now includes 9 engines on the ship itself, 3 sea-level Raptors and 6 vacuum-optimized Raptors, all of them from the upgraded Raptor 3 line. Gone is the mythical version 3 Starship we used to speculate about, the rumored 150-meter-tall monster rocket. Instead, we're looking at a real, measurable spacecraft, 142 meters tall when fully stacked. The booster comes in at 81 meters, and the Starship stage measures 62 meters. It's leaner, smarter, and clearly built with mass production in mind. Musk's updated goal of producing 3 complete Starships per day would require an output of 126 engines per batch. That's a mind-bending leap from current production levels and highlights how essential it is for SpaceX to perfect its engine manufacturing process. At the heart of this transformation is the Raptor 3 engine, a complete redesign from the earlier Raptor 2. Currently, these engines are being developed and tested at SpaceX's McGregor facility in Texas, about 450 miles from Starbase. The company hasn't released official production numbers, but based on facility activity and leaked imagery, estimates suggest they're making perhaps 4 Raptor 3 engines per month. Let's pause and compare. 4 per month versus 115 per day. That's not just a production increase, it's a tectonic shift in capability. So, how do you go from boutique hand-assembled rocket engines to building more than 40,000 per year? It starts with a complete overhaul in design philosophy. The Raptor 3 isn't just a beefed-up version of the Raptor 2, it's a reimagined machine built for scale. We're talking about 280 tons of thrust, up 22% from its predecessor. The combustion chamber pressure reaches a staggering 350 bar, far exceeding any current operational engine on Earth. And despite that power, it's lighter, just 1,525 kilograms, giving it one of the highest thrust-to-weight ratios ever seen. Even more impressive is how they're engineering it for safety and simplicity. For example, the cooling channels that used to be separate components are now integrated directly into the engine body. This eliminates the need for bulky heat shields, reducing weight and points of failure. And here's where it gets really clever. If a minor fuel leak occurs, the escaping propellant vents into the combustion stream and harmlessly burns away. No explosions. No mission-ending failures. It's a level of redundancy and foresight that feels like it was plucked from a Star Trek engineering manual. And these engines aren't just being tested once and crossed off a list. Elon Musk confirmed that over 300 hot fire tests have already been performed, racking up more than 16,000 cumulative hours of burn time. That's not just trial and error. It's systematic, data-driven iteration at a scale few other companies can match. SpaceX isn't treating the Raptor 3 as a finished product either. They're using every test to learn, adjust, and refine, building the foundation for an engine that isn't just powerful but reliable enough to build en masse. But even with the design perfected, mass production is an entirely different beast. Right now, McGregor is operating like a bespoke workshop, building engines one at a time, each one meticulously assembled by specialized teams. There's a team for material processing, another for the engine bell, others for the fuel channels, and still more for the turbo pumps, ignition systems, and exhaust plumbing. Each part is carefully machined and fitted using high-performance superalloys like Inconel, capable of surviving temperatures north of 5,000 degrees Fahrenheit and pressures up to 120,000 psi. It's not just manufacturing, it's metallurgy, fluid dynamics, and combustion science all rolled into one. That level of precision can't just be scaled linearly. You can't just throw 100 more engineers at the problem and expect 100 times the output. What SpaceX needs is automation, modularity, and an assembly line approach that's never been tried before in rocket production. Think about how Henry Ford revolutionized car manufacturing, not by building better cars but by building them differently. SpaceX is trying to do the same thing for engines. Their long-term goal is to move from heavy, bolted flanges and one-off castings to additive manufacturing, seamless welds, and robotic assembly systems. In short, the next leap isn't just technological, it's philosophical. But here's what makes this truly ambitious. They're trying to do all of this while continuing live test flights, launching payloads, and preparing for lunar and Mars missions. They're building the engine of the future while still actively flying today's version. That's like redesigning a jet engine while flying the plane. Every success gives them data. Every failure becomes a case study. They're evolving in real time, turning lessons into improvements and improvements into scalability. Even still, the road ahead is steep. To produce 115 engines per day, SpaceX will need to revolutionize not just how they design and test engines, but how they source materials, structure their teams, and construct their production facilities. We're talking about gigafactories dedicated not to batteries, but to rocket engines, humming with robotic arms, CNC machines, laser welders, and AI quality control systems. Each step from raw metal to finished engine has to be streamlined, cost-effective, and scalable, or the entire vision collapses. And yet, if there's one company on Earth capable of pulling this off, it's SpaceX. They've already shown the world that reusable rockets aren't just possible, they're practical. They took an industry where launching a rocket once was a triumph and made it look routine. Now they're setting their sights on the next impossible goal, making rocket engines as common as jet turbines. If they succeed, it won't just be a manufacturing milestone, it will change how we access space, how we build colonies on other planets, and how we define what's possible for the future of humanity. Because at the end of the day, this isn't just about engines. It's about building the backbone of an interplanetary civilization. Every Raptor 3 that rolls off that line represents a step closer to Mars, to the Moon, to deep space habitats and commercial spaceports. It's not just a machine, it's a movement. And in Part 2 we'll explore the next stage, the facilities, the supply chain, the workforce, and the broader implications of mass-producing these powerful engines, not just for SpaceX but for the future of space travel itself. SpaceX has worked hard to eliminate as many of those old flanges and mechanical fittings as possible, replacing them with sleek, laser-welded joints. Laser welding offers cleaner, more reliable seams that can handle extreme environments. Because when you're dealing with engines that face brutal heat, insane pressures, and bone-rattling vibrations, any traditional thread or gasket becomes a point of weakness. And that weakness can spell disaster. Earlier versions of the Raptor engine struggled with this exact problem. Sealing those engines tight was an engineering nightmare and leaks were constant. But now, with Raptor 3, SpaceX claims that problem has finally been resolved. The design is more consolidated, more robust, and far more leak-resistant than ever before. Still, not everything can be laser welded. There are places where 3D printing becomes essential, especially in the regenerative cooling channels inside the nozzle and combustion chamber. These internal pathways circulate cryogenic fuel to absorb heat and keep the engine from melting itself during operation. They're intricate, twisting, and nearly impossible to build using traditional manufacturing methods. That's where 3D printing shines. It allows SpaceX to create those ultra-complex geometries in a single piece, boosting both durability and performance. And that's part of why the Raptor 3 looks so much more compact and refined compared to its predecessors. It's not just an aesthetic choice. It's the result of radical simplification. According to leaked details and analysis from industry experts, the Raptor 3 is built around three primary modules: the thrust structure, which houses the interface with the liquid oxygen tank; the turbo pump assembly, which forces fuel and oxidizer into the combustion chamber at incredible pressures; and of course, the combustion chamber itself, where the magic, or the controlled explosion, happens. These modules can be manufactured either through advanced 3D printing or by machining single integrated parts, drastically reducing the number of welds and potential failure points. That change alone increases the engine's structural integrity while allowing mass production to move faster. But 3D printing isn't the golden ticket for everything. While it's powerful, It's also slow and still more expensive than other fabrication methods when you're aiming for scale. So SpaceX is focused on finding the right balance. The mission now is clear: slash cost and boost speed. Elon Musk has publicly stated his ultimate target is to get the cost per ton of thrust under $1000. That would mean each Raptor engine has to be built for less than $250,000. Compare that to the current price tag, still estimated to be around $2 million each, and it sounds almost impossible. But SpaceX believes they can get there, especially if they reach their dream output, 126 engines per day. At that level of production, economies of scale begin to kick in hard. The per unit cost could drop dramatically, maybe to $500,000 per engine, or even down to the $200,000 range. But even at that point, the math gets mind-boggling. At $200K apiece, building 126 engines a day means spending over $25 million every single day. That's a $9 billion annual engine budget. And that's just for propulsion. It doesn't even begin to include boosters, tankers, crew cabins, heat shields, or guidance systems. And if Musk really wants to ramp to triple-digit daily production, SpaceX will need more than just dreams. They'll need serious real estate. That's why insiders believe at least 5 more production facilities will need to be brought online to support the scale-up. And these aren't just assembly buildings. They'll require testing bays, materials pipelines, precision machining setups, cryogenic storage, engine stands, and transportation systems to ferry completed Raptors straight to launch complexes. You can't build that kind of infrastructure overnight. And you can't do it just anywhere. That's why SpaceX is eyeing expansion primarily in Texas and Florida. These states offer proximity to existing infrastructure, ocean access, and, perhaps most importantly, a business environment that's far more favorable than what California has to offer. Let's be honest, California probably isn't on SpaceX's roadmap anymore. The political climate and economic friction there, especially with figures like Governor Gavin Newsom, has created a lot of tension. Add to that California's notoriously high taxes and strict regulatory hurdles, and it just doesn't make sense. For a company laser-focused on rapid iteration and cutting-edge manufacturing, time lost is money lost. Every delay or bureaucratic slowdown eats into that goal of making humanity multiplanetary. So Texas and Florida it is. And it's not just about making engines anymore. Elon Musk has stated openly that he wants SpaceX to build 3 starships per day. That's an absolutely insane target by aerospace standards. And yet, it's not impossible. If each facility could eventually build a starship every 3 days, then scaling up to 3 per day across a few locations becomes feasible. But building starships at that rate also creates a new problem. Where do you even put them? These vehicles are nearly 400 feet tall when stacked with their booster. They don't fit in a parking garage. Heck, they barely fit on the roads. That means SpaceX will need huge amounts of land just to store, outfit, and launch these massive machines. And then there's cost again. Housing in California is already outrageously expensive. Now imagine trying to store, maintain, and launch literal skyscrapers made of stainless steel from the same region. The economics just don't work. That's why SpaceX's expansion is leaning into areas with open land, lower taxes, and direct ocean access for launches. That's where the future is taking shape, in Boca Chica and Cape Canaveral. But here's the thing, SpaceX actually can afford this. The company is bringing in serious money. According to Musk, SpaceX's commercial space revenue is expected to exceed NASA's entire budget next year. Think about that. NASA's entire budget for 2025 will be around $25 billion. And SpaceX is closing in on that mark just through launch contracts, Starlink subscriptions, and satellite deployments. This year alone, SpaceX is projected to earn about $15.5 billion. Of that, only $1.1 billion is coming from NASA. The rest is pure private sector hustle, telecom deals, commercial launches, defense contracts, and expanding Starlink internet across the globe. But to build the kind of future Musk envisions, to make Mars not just reachable but livable, they'll need to push further. Building over 100 Raptor engines per day won't happen overnight. Even with SpaceX's warp speed engineering culture, we're probably 5 years away from hitting that number. For now, they're focused on getting their second major Starship factory online in Florida. Combined with the original site in Texas, these 2 mega facilities are just the beginning. Once both are operational, they'll be capable of producing a full Starship roughly every 3 days. But the real goal is far more ambitious: 1 Starship per day by the year 2030. And to support that, Musk wants to scale Starship manufacturing to the same level as Boeing and Airbus build airplanes. That's not a metaphor, that's the actual target. Boeing and Airbus each produce hundreds of jets per year, and Starships are bigger than any of them. Even the mighty A380 looks small next to a full-stack Starship. But SpaceX plans to match that level of output, because to build a self-sustaining city on Mars, you'll need thousands of launches. Not dozens. Not hundreds. Thousands. That also includes building out the communication infrastructure to support life on another planet. Right now, SpaceX produces about 5,000 Starlink V3 satellites per year. These newer models are roughly the size of a Boeing 737. They're huge compared to the earlier versions and pack far more power. The goal is to double that production rate to nearly 10,000 satellites per year. That might sound like overkill, but it's not. To build a data bridge between Earth and Mars, you'll need redundancy, low latency, and global coverage, plus a whole network around Mars itself. All of this builds toward Musk's roadmap for Mars. By 2026, the plan is to send 5 Starships to the Red Planet. Each one will carry about 10 tons of equipment. That early wave is just to test the waters, to prove they can get there, land safely, and communicate back home. From there, things escalate quickly. In the 2028 to 2029 window, SpaceX wants to send 20 Starships, each delivering around 75 tons of gear. That's when they begin setting up infrastructure, scouting for water, and preparing landing zones. Then around 2030 to 2031, the real work begins. SpaceX hopes to launch 100 Starships, each carrying 150 tons. At that point, it's no longer about exploration, it's about settlement. They'll be mining local materials, building shelters, laying roads, and generating fuel using Martian resources. This is where the backbone of a functioning outpost starts to emerge. Finally, in the 2033 window, the boldest step yet, a fleet of 500 landers, each hauling 300 tons. That's 150,000 tons of cargo dropped on Mars in a single launch window. Enough to build habitats, power stations, food production, and autonomous factories. It's the moment Mars begins to become independent. That kind of effort, on that kind of timeline, is almost hard to believe. And yes, it will probably take longer than expected. Maybe we won't see real Martian boots on the ground until 2035 or beyond. But that's okay. Because the size of the dream demands patience. And the scale of the ambition demands resolve. Even if we're still years away from liftoff, what SpaceX is doing right now, today, is laying the foundation. Every Raptor built, every Starship stacked, every launch rehearsed, it's all moving us closer to that distant red world. And maybe, just maybe, Starship Flight 10 will be the spark that proves this insane vision is possible. The rocket that whispers to humanity, this isn't science fiction anymore. This is just the beginning.